Good afternoon, guys. My name is Wayne. Welcome to this talk. I work in the R&D department of Unity, and you've come to the best talk of the whole Unite. I'm going to talk about how we did audio and how we built an audio engine in ECS for the Megacity demo. And to do that, I need to talk about two separate things. The first one I need to talk about is our new audio rendering engine called DSP Graph. A low-level rendering engine that we built. And the second one is how we actually built this entire audio stack on top of ECS for the demo. So what is DSP Graph? I guess this is a new term for a lot of you guys out there. DSP Graph is ultimately a new sample rendering engine, a new audio mixing engine for Unity. We hit a lot of scalability issues when we were trying to implement features on our old rendering engine. So we had to kind of take a step back, start from scratch, and rewrite this engine from the top. So what is an audio rendering engine, or what is an audio mixing engine? If any of you guys know what DSP is, basically you've got DSP nodes in a DSP signal graph. Those DSP nodes can be anything from reverb to echo effects, limiters, stuff like that. They do their work, they produce some sample buffer outputs. Those sample buffers are mixed together with other sample buffers, more effects are applied, so on and so forth, until eventually you've got a sample buffer that goes out of the sound card, and that's what you hear in the games that you play and love. So ultimately it's the lowest level kind of feature or audio rendering that you can do, or that you need. And this is what we kind of had to rebuild. Our entire new audio rendering engine is written in C#. And all of the DSP nodes that we write and that you guys will write and all that sort of stuff will be written in C# as well. And I guess a lot of you are probably immediately thinking, okay, so what about the performance characteristics of writing DSP kernels in C#? And the great thing is that we're going to be leveraging the new burst compiler technology so that all of the DSP that you write will be highly performant on all of the platforms by default with native code, like vectorized execution and stuff like that, which is really cool. So what we are actually building here at its core is an audio system in C# at the lowest level. All of the effects, graph structure, parameters, all of those things we'll be writing in C# in a package. The entire audio system will be a package that we can give to you guys so that you'll be able to dig down as far as you want into it. There's going to be no hidden runtime code. There's no things that you won't be able to get your hands on and access if you want to dig deep enough. And with all of this, these new compiler technologies and all of this cool stuff that we're doing with the C# job systems and all that sort of stuff, there's absolutely no performance penalty. In fact, as I'm going to show, we're actually doing pretty well for performance. It's a totally extensible engine at its core. I'm going to show you a few of the features that make it, and sort of you'll be able to leverage to make it as extensible as you need. And it's ideal for procedural sounds that are being driven from game logic, music systems that you want to sample accurately beat match, third-party sample libraries that you need to interface with. Anything that you want to do in terms of audio, you'll be able to dig right down and get to with DSP Graph. And it's a foundational API that we'll be rebuilding our entire audio system on top of. We won't, like in the coming months, you'll see more and more features built on top of DSP Graph as we release DSP Graph. More building block foundational APIs, editor tooling and stuff like that. The actual DSP Graph itself is a very low-level engine. I mean, think sort of graphics API kind of thing. So it's not for everybody. It is there if you need to get to it, but we'll be supplying a lot more user-friendly, higher-level concepts on top of it. But one of the reasons why we're trying to build this engine as a sort of user land engine is that we never have to tell users, never have to tell you guys, you can't do that in Unity. Like, we want to be able to say to you guys, you can do anything you want in Unity in terms of audio. It really just depends on how deep you want to dig down into the engine. It fits neatly into the execution model of the rest of Unity. It's fully jobified, but those jobified characteristics can be configured. Maybe you want to use the entire job system for graphics or culling or physics or something like that. So you can, pare down all of the jobified execution of the graph down to the audio thread if you want. All of these characteristics will be completely configurable to you guys. All of the interactions with the graph will be completely lock-free. We're not going to be stalling the main thread. We're not going to be hitching anything, sending commands, sending changes to the audio system. It's going to be completely hitch-free. I mean, we needed to hit 60 FPS on this demo, so it had to be completely asynchronous and lock-free. All of the commands are going to be bunched up into transactions. It's important that when you interface with a asynchronous audio system, that as you're making changes, you want those changes to be completely atomic, instead of the audio system coming up, doing a mix while you're halfway through, and you getting something that you really didn't expect from making changes to the DSP graph. And what we're seeing here already is orders of magnitude speed up over the traditional on-audio filter reads that you would have done in your audio system, audio DSP in the past in Unity. And what it also means is that you won't have to muck around with audio plugins. You won't have to muck around with DLL hell, compilation of external libraries, all of those things. This is all going to be completely open and automatic for all of the platforms that you target with DSP Graph. You just flick on the burst compiler flag and we take care of all of the heavy lifting for you. And we've also created a completely new revamped way of reading samples out of audio clips. Obviously jobified, obviously highly performant way of actually pulling the samples out of the audio clips and feeding them into these DSP jobs for audio clip playback. And when we're talking about performance here, I'm just going to throw random numbers up. When we're talking about performance here, we're not even talking in the same sort of game as the old audio system. On my machine here, it's a relatively new MacBook, I'm able to stream, decode, and play back 1,000 Vorbis compressed audio samples at once. I mean, we're not even talking about the classical 32 sound playback that we had with the old audio system. I mean, given that we're completely jobified, completely asynchronous, we are really able to push the machine to its limits in terms of the new audio system. Talking about performance, we need the obligatory, profiler screenshot. And one thing to note here is that, each of these jobs fits nicely into the job system if you want. All of the execution of this is nicely jobified. The audio thread and all of the audio work now is completely profiled. So you'll be able to dig in, see where things are working, see which effects are taking too long, where mixing is a bit too heavy, and make adjustments to your really low-level kind of mixing concepts as you go. And as I was saying before, in terms of jobified audio clip reading from an audio clip now doesn't actually decode on the audio thread. In fact, it pulls from a decoded sample buffer, and then at the end of a mix, we launch a whole bunch of asynchronous jobs to backfill those sample buffers. So we're completely kind of decoupling a lot of the concepts into asynchronous jobs. So let's take a look at what actually, how do you do one of these graphs? What is a graph actually? So returning to our mixing graph before, it is a directed acyclic graph, meaning that you can have all sorts of inputs and outputs from nodes. And what we've done is we've wrapped this entire concept in a DSP graph container. The DSP graph container name represents the kind of highest level concept around this whole thing. And all of these DSP nodes and DSP sample buffers and edges and connections will be, and parameters and stuff like that will be contained inside a DSP graph. And as you can see, I've got a link to the sound card here, or to the output, but that actually isn't necessarily even necessary. Isn't necessary. These DSP graphs are absolutely decoupled from the audio device. They can be driven from script. They can be fed into other DSP graphs in terms of the sample output. They can feed into on-audio filter reads if you wanted, or third-party libraries, or whatever. It's completely flexible with what you can do with these new DSP graph containers. And it means that what we're doing ourselves is we're completely decoupling DSP graph from the audio device. So now the audio device becomes more of a sample sink that can, pull samples from DSP graph if it wants, or produce white noise. I mean, whatever you want, but we've decoupled these two concepts so that you can really, drive DSP graph by yourself for recording purposes. You don't want to actually output the samples to the device, and all those sorts of things. Very, very flexible. I'm just going to go quickly over some code. It's not really important what the code is, but just to give you a kind of a concept, an idea of what's going on. You can create a DSP graph from script using any audio parameters or any audio parameters that you want. That graph, you can then begin a mix. It will launch a whole bunch of jobs in the background for you, doing all of the sample mixing and job creation and all that sort of stuff. You can come back later, create a native array and read the produced samples out of the graph. So you can see, like, immediately the DSP graph is useful, perhaps not even for audio concepts. You can do all sorts of interesting things with any sort of sample-based media. Just a quick note, I wouldn't bother writing any of these things down. We actually had a whole bunch of feedback from working on the demo. We're going to change the API a little bit as we go. So the final API is not going to look exactly like that, so don't get excited. DSPNode. How do we actually create, manage, and deal with one of these sort of kernels? This is the sort of brain of what DSP Graph really is. And DSP nodes themselves can have any number of inputs in terms of sample buffers, any number of outputs. Every one of these inputs and outputs can have any sort of channel configuration, which is extremely powerful in terms of being able to mix half of the graph in terms of mono and then spatialize out into ambisonic or stereo or 7.1 or whatever you feel like. The sample buffers are available to the execute function. They're passed into the job execute function. And a job's responsibility, if any one of you are ever going to write one of these audio jobs, is that you take the samples from the input, you do a whole bunch of work in the execute function, and you fill out the sample buffers for the output. That is the contract, basically. And with that, and linking all of these guys up, you can create a very, very powerful audio system. Any one of these input ports can have multiple input connections. All of the samples are auto mixed together in this case, and any one of these nodes can have any one of these ports can have multiple output connections as well, which is really cool in terms of being able to split the mix and do all sorts of different things with it down the signal chain. Each one of these nodes can define a whole bunch of parameters, and parameters are a very cool and interesting way of automating properties within your DSP nodes. These parameters can be sample accurately changed or modified or automated over time in a scheduled way, because you've got to remember here that audio is being mixed asynchronously on another thread, but you can schedule parameter changes and automation in a very sample accurate way. And as an example here of this, with this ducking node, let's take the threshold we can actually modify the parameter, modify the threshold from -40 to -15 between DSP clock X and Y. So you can schedule this ahead of time, and then as the DSP graph goes along, processing, it hits these clock values and then will automatically interpolate this value for you. So it's very powerful, sample accurate automation. As I was talking about before, in terms of efficient reading from audio clips, we have created a new concept in terms of sample providers. Every one of these audio clips, you can create this new sample provider concept and read from these audio clips into the DSP nodes. So this is how you create sort of voice playback, clip playbacks. And a really powerful tool and necessary tool for interacting with the rest of Unity and the other subsystems is the ability to post events from inside a running job. If you come up to something interesting, maybe the RMS value of a particular sample buffer reaches a certain level, or a clip has looped, or a clip has stopped, you can actually post an event to a bunch of handlers or actions that you've registered with a DSP graph on the main thread, and be able to take the output or that event and do something with it. Perhaps modify a wind zone or change the way a car is moving or something like that. So now we're able to see that you can get some really tight coupling between the game itself in terms of the other subsystems, the other physics, all these other subsystems, graphics, and audio itself. Audio could drive, for example, the audio signal could drive a particle effect in terms of wind. So you can have random wind sounds playing, and then all of a sudden the particle system is driven by the actual sound itself. Taking a look at how you would actually build one of these guys, it's an interface that you implement, much like iJob or in any of the other iJob concepts, if you've used the C# job system. And the execute function here takes this execute context, and it has everything you need in it in terms of input, output, sample buffers, the sample providers I was mentioning before, parameter automation, all of those sorts of things. So let's create, actually, just quickly, one of these guys, just to give you an example of what's going on. Let's create a player that reads samples from a sample provider, an audio clip, and applies a gain to those samples on the output, and it pushes those samples to its output, and which are mixed somewhere else in the graph. Of course, we put this burst compiler flag on so that we get really native performant execution. And taking a look at how you would actually pull samples, it's really, really quite easy in terms of being able to just get the output buffer from the context, get the sample provider from the context as well for this particular source clip sample provider, read the source samples into the output buffer, and then apply a gain to the output buffer in terms of getting this float value based off its offset in the sample buffer. So again, sample accurate automation. And what we're creating here is a simple audio source. You can see that it's very basic, there isn't much to it yet, but already we've got the foundations of a new audio system written in C#. So, the future of audio. What is the future of audio in Unity? Where are we going with it? Unity Audio is definitely C#, and in that, it's also fully accessible to all of you guys and to anyone who wants to build on it. It's deeply featured. I mean, we're really pushing to have all of the features that we really missed in the old rendering engine. And of course, it's performance by default. That's what we're going for with Unity in general now, and this is, of course, where we're going with audio. So, now with that introduction, how did we actually build an audio system completely on top of it in ECS in 2 months? I can tell you that it was pretty daunting. But we kind of knew that we had a couple of things up our sleeves. We had DSP Graph, we had ECS, so we had this performant framework stuff. We also had the new audio clip reading functionality and new prefabs. The new nested prefab system was also a massive gain for this demo. What we didn't have? Well, we didn't have physics, we didn't have trigger boxes, gizmos, audio sources, we didn't have any mixing graph UIs. We didn't have any DSP effects already implemented. We had to implement our own reverbs, resamplers, panning, which in the end was of course all written in C#, but still we had to do it. And we didn't have any profiling tools either, which was a challenge. So what we did, we had a look at the demo in its infancy, and we identified 4 main categories of mechanics when it came to sound output. Of course, we wanted a music system. We wanted to have a really dynamic, interesting music, musical landscape within the game to give that punchy kind of emotive feel as you're flying around. We wanted the vehicle itself to obviously make noise. You're controlling a vehicle. It needed to make its own little futuristic car sound. And the environment and the traffic. Traffic is made up of a whole bunch of entities, a whole bunch of sound points. We had to create these sounds. And these use this concept of sound fields, which I'm going to go into shortly. I was going to... one more thing. We had an actual 5th mechanic that we had to create at the last minute, which was this flyby concept. The sound designer and us sort of agreed that flying past cars wasn't giving the kind of punchiness that we were hoping for in terms of getting that whooshing sound. So we created a very specialized flyby system for when your car interacts or comes close to one of the cars in this 5,000 agent car system. So I was going to give a live demo, but my technology isn't working right now. So what I'm going to do instead is I'm just going to play a short excerpt from the keynote yesterday. I don't know if none of you saw the keynote or have no idea what I'm talking about in terms of Megacity demo. I'm going to play a short part of it so you get a feel for what's going on in terms of the demo and the soundscape. So you can see, you can hear as we're whooshing past the different elements within the game, a lot of these elements are coming in from the prefabs and the buildings themselves.
So look at all those cars. There are 5,000 separate AI agents, all flying on these traffic lanes, avoiding each other and the player.
You can hear a transition of music down to a more subtle experience. Cool. So that gives you an idea of kind of what we're building with those 4 or 5 mechanics. So let's talk about sound fields and what that actually is. We talked about environment sounds, traffic sounds. We talked about the scale of the Megacity demo. And the Megacity demo was streaming in tons and tons of entities and streaming out tons and tons of entities. That was the whole point of the demo. And so we had to reduce these huge amount of emitter points into a sort of a workable soundscape, which is a bit of a challenge. At any one time, we had over 100,000 emitters that we were dealing with in the game. But playing back 100,000 individual audio sounds wasn't really feasible, but also isn't even really desirable because, I mean, if you've done a lot of sound design, having 100,000 clips play back at once ends up just as loud white noise. So we didn't want that. We needed to pare it down into something more reasonable. And this is where sound fields came in. We needed to reduce the polyphony. We needed to take this huge soundscape and play something that made a lot more sense. What sound fields are, imagine a scene with all of these prefab instances just scattered around everywhere. And each one of these prefabs is of a particular type. You can imagine like your neon signs, your AC units just scattered everywhere. The neon signs play a little bit different sound to the AC unit, of course. So they're kind of like grouped into these clusters of types of sounds. In this particular graphic, you can see the different colors denote these different types or these different groups. So you assign an ID to these particular groups and then isolate them. You isolate a group into one single voice playback, and you then play with that kind of group and pare that down into a single kind of panned emitter. Each one of the sound field emitters contributes some amount to the left and right panning of the listener in terms of if all of the sound emitters are in this cluster over here, it will pan nicely over into like a group over here. But contribution from each sound emitter is calculated based on its distance from the listener. You can see as things come closer to the listener, their contribution outweighs those things that are more distant from it. So ultimately speaking, as something comes whooshing by really close, that dominates the sound field mix completely. So you still have this nice feeling of 3D kind of immersion as you fly past one thing, you get it contributing completely to the mix. It flies by in 3D, and then its contribution is calculated frame by frame back out into the main sort of cluster of the sound field. Under the hood, what we're doing is as we said, we take these whole bunch of emitters in this group, we map reduce those huge amount of emitters down to a single voice, or a group of voices. We had like groups of emitters that like there was a bunch of AC units, and there was about I think 5 or 6 different AC sounds that were randomly kind of peppered throughout the scene. So those contributed as one single voice, and they were all assigned a particular ID or a particular group. Anyway, you've paired these emitters down to a single voice playback. That voice playback then starts interacting with the DSP graph through this command block. And the command block basically defines how we do this asynchronous transaction to the running DSP graph. And from there, like from this system, we can now automate things like the left-right balance of the mix, the front and back balance, and we actually did front and back panning using low-pass filters. We also have obviously contribution to reverb. We need interesting reverbs as we go through the tunnels, back out into the open space. We tone the reverb down, and all of the volumes and everything are controlled to the output as well. So these voices control a lot in terms of not just clip playback, but effect parameters and stuff like that. Let's take a look at what actually, what are one of these prefab entities? You've got an AC unit. What does it contain, or a street lamp here? So it contains a lot of different things. Obviously, your transform, your mesh render, and everything else that you needed by the other subsystems. And it also contains one of these EC sound emitters components. And what that defines is its material, its sound material that it's using, and its voice allocation, and a whole bunch of other things. I'll get into sound materials in a minute. But what's cool as well is it also adds this tag component, which is the play state. And what we can do with this play state is define when a sound should be playing or not. If we want a sound to play, we just add this component to the entity, and then using the power of ECS, we can filter down only the entities that actually are in this play state in a very efficient and simple way. So one of the things that we also had to deal with, like I was saying before, is we're streaming in thousands of entities and streaming out thousands of entities every frame. So we needed to deal with handling sort of system state for all of these entities in terms of allocating resources, deallocating resources when we stream out the entity. So in terms of how that works, we use system state components, which are a new feature of ECS. And in system state components, you stream in an entity. It has a component that you can filter on, and we attach these system state components alongside this other component. And what happens is when you actually delete or kill the entity after it's being streamed out, that system state component stays. That entity isn't actually destroyed until we come along, detect that you've removed or you've destroyed the entity by removing the original component, and then we can come along and actually pare down the resources, deallocate all of the resources from whatever system we need, and all these sorts of things. So we used heavily system state components for the streaming in and out of these entities. When a new entity comes in, it only got this EC sound emitter. When we're running, we've already injected the playback state, and once we dispose the entity, we've only got the playback state, which we need to get rid of. Okay, so what we actually built as well on top of this is a completely separate voice playback system. All of these different mechanics obviously produce sound or wanted to play sound, but we had a completely different system that actually managed those voices, a different component system, which is really powerful actually. All of these different concepts would say that they wanted to create a voice, a playback instance. They would create a new entity with this voice instance component, and this would be picked up by our playback component system. The playback component system was its own kind of management system for all of these voices. It would detect that we haven't actually created the voice yet. It would insert its own system state with all of the DSP node information and stuff that it's allocated, and then manage that voice through all of its life cycle. Once the voice finishes, say with the flyby system, we have DSP Graph, the DSP nodes sending events back to the main thread, which is picked up by the component system here, which then destroys the entity, which allows us to destroy the resources, so on and so forth. So it's a really powerful system, all in one, and it allows us to do cool things in terms of voice management, profiling. We can see what's happening in this component system as one single thing. We don't have to worry about, the voices are coming in from the environment system. We can't see how many there are there and how many of the engine ones and blah, blah, blah. It's all in one self-contained area. So the city environments used these sound fields, as I was describing before. And they had a whole bunch of interesting 3D properties, like roll-off distances based on how far you are away from the entity, cone angles for directionality. We actually have like a cone system now in terms of being able to direct sound and spread it out. But these properties themselves weren't actually stored on the component. We developed a material system so that you could define a sort of a material asset which defined all of these 3D properties, and then share those properties between different instances of these prefabs throughout the world. You can imagine that you've got AC units up at the top of the world, up to the top of the scene, where you want to have different 3D characteristics to when they're at the bottom, towards the clutter at the bottom. So you can assign different materials based on where they are in the world, and then modify those properties all in one place, which was really, really powerful. Yeah, like I was saying, those 3D properties can be modified all in one place and then shared between all of the instances. So I'm just going to play a demo of this whole thing and giving you a kind of a run through of how these gizmos and cone angles kind of operate. And see here I've got 3 instances of, cannot hear the playback, should I turn it up? Okay, cool. And you can see here that we actually have the opportunity to modify these properties in real time through the asset. Change the cone angle all the way out, back in again, change the roll-off distances. All of these things are completely configurable in our system, which was super important for being able to rapidly iterate the sound design throughout the level. Just a second example here of this in action in a couple of city blocks. You can see in that demo on the right, we quickly kind of prototyped a graph debugging tool. You can see all of the colors of the noodles changing based on the left and right panning of the system. Each of the nodes, you could see the RMS values, different parameter settings. All of these things were sort of debuggable and viewable, which was really helpful when we were trying to build this thing. This debug tool was just quickly whipped up in the project itself, but really shows you how powerful having a user-land audio system is, because you can really dig in and see every single parameter, every single element of this DSP graph from a user-land project and from this quickly prototyped UI. Traffic also used the sound field concept. Obviously, these sound fields, these entities were not static. They were moving as the agents were moving around the world and avoiding each other and that sort of thing. But what's interesting with the traffic sound fields is that it gave us an opportunity, they were modeled as point sources. There was no directionality for these particular ones in terms of cars. They just emitted in all angles. There was no cone or any of these other properties, which we didn't really need for car sound propagation. But it was an entry point into the flyby system. It was something we had to create last minute just to get those punchy sort of flyby sounds as we're zooming past other cars. And this was actually probably one of the most complicated systems that we had to build. We initially built it so that, as when we're in the traffic sound field system, we would detect, close proximity to any of the other entities. We'd have to quickly pre-process any of the candidates that we had in terms of, okay, so this, we had to cull things out, like based on Zoom cars that are out, way distant from where we are in the world. We had to limit the amount of voices that were being played. We couldn't have too many flyby sounds happening at once. We had to ignore sounds that were already playing from another flyby instance, blah, blah, blah. And then once this was pre-culled, then we're able to spawn a new entity that defined the flyby instance. And that entity was then picked up by the specific flyby system, component system. The component system would then do additional calculations in terms of, relative velocities and intensities from the flybys. So different cars had different intensities. The small little cars had a weaker intensity compared to flying by some of those big carrier units. we'd bucket those sounds or those flyby entities into relative intensities, apply a whole bunch of other characteristics, volume, pitch, and other things that, it was a lot of tweaking to get the flyby sounds working quite well. And then, again, once these were all defined, calculated and whatever, we would then go away and create the sample playback instance. So just to have a quick look at what that looks like in terms of, we have a world here which just has the car zooming around. We can fly around. You can see the flyby instances coming into and out of existence in this profiler. These other playing instances in the profiler are actually just the general sound field of the traffic itself. So we've actually only got like 8 traffic sounds playing at once. But these flyby sounds come into existence as we get close enough and zoom past each one of these cars. Music and the player vehicle controller were a lot more simpler in terms of scalability, because we only had one kind of music playback, so there was one entity in terms of music playback and also with the vehicle controller. But it was still interesting in terms of how we implemented the music from a sound design point of view. We really wanted to do vertical mixing with the music. Vertical mixing is basically the ability to increase the intensity of the musicscape by introducing additional sample accurately aligned instruments, bringing in more and more instruments to increase the intensity of the mix, and then bringing these instruments out back down to a subtle level when you want to decrease the energy. We wanted a system where as you were flying around the world, you could transition between different intensities based on where you are. So imagine sort of flying out into the open space, open trench with all the cars zooming by. We wanted to increase the energy right up to give that sort of, emote that sort of like wow feeling. And then as you sort of fly up above the city, we wanted the intensity to drop right down. And you sort of saw that in the video. We wanted that intensity to drop right down so that you could just sort of get this more pensive look over the city. So these were done by these trigger boxes, and each one of these trigger boxes was assigned an intensity value. These trigger boxes, we would write a component system that detected when a vehicle was in the bounds of a trigger box, and if it was, then we told the music system to crossfade in different samples based on what that intensity value was. And the vertical mixing, basically we had a whole bunch of different instruments that we assigned to the different intensity levels, and as we went on, as we increased the intensity, we just brought in different instruments so that we could increase the energy, which was it's a really cool way of kind of having a very dynamic music system. So another demo. Here you can actually see the trigger boxes, and as we fly in, we fade in a lower intensity of the music, and then when we fly into the second trigger box, fade in more drums, and then we fade out the entire mix altogether as we transition into an intensity of 0. The player vehicle system. Okay, so again, was a single entity. The component system really didn't have to do a lot of work each frame. Not as many as 100,000, but it was cool because we were actually demonstrating how DSP Graph could apply a whole bunch of different parameters from the outside game, which is basically what was happening with the car in terms of pitch, roll, and speed and all that sort of stuff, and drive DSP Graph in this very sort of sample-accurate automated way. So what we built was a system where you could define a bunch of layers or elements. Each one of these layers defined a playing clip in terms of a part of the engine, a part of the the car's engine soundscape. You could define a bunch of different volume automations, pitch automations. We had 2 EQs for each one of these sounds that did a whole bunch of EQ changes, and each one of these automations was controlled from something in the outside, something from the car. Like, for example, the velocity, the pitch angle, and when we were doing a barrel roll, those sorts of things. So that was a really cool mechanic that we kind of threw together very quickly. It worked really well, actually. It kind of it needed a few tweaks to get the sort of sound right, but yeah, it came together well. I'm just going to give a quick demo, last demo of the talk. You can see the little noodles, the yellow noodles coming in and out as we sort of zoom around, fade in different aspects of the mix based on the velocity, angle of the car. Parameters are being changed on the EQ in terms of how much EQ you want at each level. Yeah, and all of that is being mixed together eventually into a gain node, into a limiter. We had a limiter on the whole mix, and then out into the output of the sound card. So that's those are all of the systems that we had for the audio in the Megacity demo. We really enjoyed doing it, and we really want you guys to be able to play with it. So yeah, it's coming in 2019 once we clean it all up, and we really hope to see good things with whatever you do with it. So thank you. Any questions, go to the mics at the back. Otherwise, yeah.
One question. Are you planning on adding in support for position to go along with the audio data to support Atmos mastering on the film side of things?
Of course. I think like now that we've kind of rebuilt the engine and made it so open, these sorts of aspects we want to be able to implement as we go along and build new features on top of this DSP Graph stuff. So yeah.